So our second speaker for the session is Nicole Mücke. She's a professor at the Technical University of Braunschweig. She's a professor for statistics learning and
Thank you very much. I'm sorry, there's some construction work in the background. I hope it's not too noisy for you. So I'm going to talk about learning operators today, in particular learning linear operators and some recent developments and motivations for this. This is a joint work together with two of my colleagues, which is Mathis Mollenhauer, currently at the Freie University in Berlin, and also Tim Sullivan from the University of Braunschweig. So at first, I'm going to give you two motivating examples where we actually have to learn operators, in particular linear operators. Then I'm going to show you how our approach to this problem is. And finally, at the end, our goal is deriving learning rates or learning bounds, which hopefully are optimal in a minimax sense. So let's first take a look onto functional regression. So this is a kind of old problem already in statistics. So in functional linear regression with functional response, so I'm focusing here on functional response, which is more a recent development compared to what was going on 20 years ago. So we have a kind of, it looks like a regression model here, where we want to learn an output y, which belongs to some L2 Hilbert space on a compact domain. And we want to learn here, in fact, an operator, which is an integral operator with respect to some unknown, let's call it kernel function f, and apply to the input function x, it looks just like this here. So this is a classical integral operator. So what we want to do in general is in functional linear regression, we want to learn the operator, the integral operator. But typically this problem is kind of boiled down or traced back to learning a function which lives in a different space, right? So the function which you want to learn belongs to some classical, maybe L2 Hilbert space, while an operator also can belong to a Hilbert space, for example, Hilbert-Schmidt operators. But still the learning problem is a bit different. So learning a function and trying to find error bounds in an L2 space on a functional level is a bit different compared to learning an operator. So there are really a couple of research approaches for tackling this problem. So some of them are really classical already and not what we consider as modern currently. So traditional approaches, I just want to mention them here, are by representing the functional data with respect to an expansion with a certain basis, like Fourier basis or B-splines. So this is super classical. Then there are also some approaches which adopt a classical non-parametric view from statistics, which involves classical kernel estimators. And also a more machine learning oriented approach would be to apply regularization techniques. And so I'm going to expand a little bit on this because this is related to what we are going to introduce later. So when you want to apply some regularization approaches, then you have to assume some assumptions for the function you want to learn. So one classical assumption is, or one method here is to apply kernel methods, which makes your regularization solution very easily to implement in the end. So here you have to assume that your function you want to estimate in order to get your operator learned, that it belongs to some reproducing kernel Hilbert space pointwisely for any point here on my compact domain. And one tries to minimize here a classical functional that looks like a rich regression functional with respect to a certain penalization term here. And of course, you want to involve some given data. And here your data, this is maybe a bit different from classical regression problems, is your data are now functions. But still you can make sense out of it by just considering here the L2 norm. Okay, then we can write it down explicitly. So this is the great advantage of taking your kernel methods. So you get the solution in terms of an extension involving the kernel and some coefficients, which you can calculate directly by solving here an inversion problem. And with respect here to what we call the empirical covariance matrix. So this is a matrix that depends on the data, which are perfectly given here, the input data or input function, and also the kernel. And this is how it works classically. And so this is nothing else than what we already know from non-parametric regression. It's just an ordinary ridge regression problem for which you can also derive learning rates. The solution operator then is now given, of course, here is a good approximation would be then considering now the integral operator associated to the learn function. And if you choose your regularization parameter, like 1 over square root of the sample size, so this is also the classical that you get from non-parametric regression, you finally end up in getting a rate of convergence for the prediction risk here. So you take the expectation with respect to the input functions, and you finally get this kind of optimal rate of convergence. So this is one example where regularization is worked out explicitly, but only with the first stage data set, or what we call the first stage data set. The first stage data set is just an IID sample, which we sample from an unknown probability distribution. But of course, we are dealing here now with function, and somehow we can only evaluate the functions at discrete data points. And doing this, this is the second stage data, and classical approaches do not really take this into account. So somehow you want to have a grid where you evaluate your functions, and this grid should be also so your result should not that much depend on the kind of discretization you employ here. So in classical approaches do not take this into account. So that's why I want to mention here some a more modern approach to this, which is nonlinear functional regression. So there is a very recent paper by some authors here, and what they also adapt here, which is a new development. So you really consider the problem of learning like a supervised learning problem, where you want to minimize here what we call the risk or the expected risk over some hypothesis space. And in the setting of functional regression, your input domain consists of functions. And currently, so the research here is in early stages. So this is sometimes also just considered as a compact subset of some Bézov type space, for example. And the hypothesis space is a class of, so in this paper, a class of ReLU, deep neural networks. And this would be a more modern approach to this problem for solving operators. And then following the path of supervised learning, you would like to solve this empirically, and you can employ an empirical risk minimization strategy. You're also given some data, which are IID data coming from an unknown probability distribution, and employing here a certain type of class of deep ReLU nets. There are some first results for solving this, and you get rates of convergence here, which look not perfect in my view. So there is the log n divided by log n and a certain power, and this power also depends on the smoothness class here of your input function space, the dimension of your domain of definition of your functions, and also some other parameters. But still, it's I want to mention here also this stream of research, because this is really currently an active field of research, which reproducing or some kind of results which is somehow really close to what's going on in supervised learning or non-parametric regression already, in the classical sense, and also employing now these powerful neural network frameworks also for learning nonlinear operators. So the second example, this is in fact the motivating example for what we are doing later. This is about conditional mean embeddings. So conditional mean embeddings also give rise to operators which you want to learn, the conditional expectation operator. So here I'm starting a bit more classically. So I have an input and an output space. And these are polished spaces. So we need a little bit of structure of these spaces in order to do inference and statistics. And also, so I'm following supervised learning programs. Okay, we have a set of input and output random variables on an underlying, they're defined on an underlying probability space. And on this here, we have a Markov kernel. And then the conditional expectation operator is defined as an integration of a function with respect to the Markov kernel. And you can write it, in fact, as a conditional expectation given x. And in this framework, okay, learning the conditional expectation operator can also be boiled down to learning these Markov kernel, in fact, and so these learning operators is also again with respect to learning a different kind of object, which is not in fact an operator anymore. And conditional conventional approaches involve here density estimation, for example. So, but there was also recently a different stream of research that applies here conditional mean embeddings. And again, I'm using the powerful kernel framework or reproducing kernel framework. So we equip our output space this time here with the kernel. And this kernel generates a reproducing kernel Hilbert space. And then one can define the conditional mean embedding. I call it here G star. It's an L2 function with respect to a certain Markov kernel here as an integral over this kernel now with respect to the Markov kernel. And this is, again, you can express this integration here as it's just nothing else than the conditional expectation at this point. What comes into play here and what makes this problem a bit more easier is that we use the structure of the reproducing kernel Hilbert space. And you can write it, this conditional expectation here, or the conditional expectation operator can just be written by the reproducing property as an inner product between the function I want to integrate and the conditional mean embedding G star. And this is what you call maybe the kernel trick. It makes the problem of learning this operator P more easily, and instead of learning this operator P, we just have to learn the conditional mean embedding G star here, which is again just learning a function. Okay, this is also the main idea here. So learning the operator means learning a function also for this example. And so in particular, I want to mention here these two works of Lee and Mattes and Peter Koltai recently. They were analyzing also this problem setting, and they wanted also to check if they can apply regularization approaches, which we knew classically also in supervised learning problems. And they started here to identify the space of Hilbert-Schmidt operators between two reproducing kernel Hilbert spaces. And they found out that for a certain kernel K that maps from some input space into the bounded operators on some reproducing kernel Hilbert space here in this case. So you define this kernel in a very special way. So you take a classical kernel on the input space and just consider the identity on my output Hilbert space here. And this is a kernel that generates, again, a vector valued reproducing kernel Hilbert space. And it turns out that this vector valued reproducing kernel Hilbert space is just isometrically isomorphic to the space of Hilbert-Schmidt operators between these two RKHSs here. And any function in this vector valued reproducing kernel Hilbert space can be represented as applying a Hilbert-Schmidt operator to a kernel in the input function space or on the input function space. And this allows now to analyze the learning problem for conditional mean embeddings. in a very nice way. So ideally, we want to, again, use data on the input and output space we have. And what we need here for the theoretical and also for the practical analysis are very classically, again, the uncentered covariance operator, which is the expectation of here the cross product between my kernel on the input space and the cross covariance operator expectation between here the cross product of output and input. And then it turns out, when you do some math here at this point, that the conditional mean embedding has a closed form expression, which looks very nice somehow, and it's very nice to have it, in fact, that involves here the covariance operator and the cross covariance operator. So this here is the generalized inverse of the covariance operator. Star means the adjoint, and you just apply it to the kernel. So, and assuming that here this G star function belongs, in fact, to the vector valued reproducing kernel Hilbert space and is known as the well-specified case. So this solution here, or the closed form expression, looks very, very promising for one reason, or for two reasons maybe. So because it involves here the covariance operator, we can very easily approximate this covariance operator using our data by replacing the expectation here with the finite sum, or with the average over our input data and output data. And then what you can do here again to solve this problem is you can apply classical regularization methods again by reformulating this problem of finding this G star, or of estimating the conditional mean operator, by rewriting this as a classical regression problem, but vector valued in this case. And it looks like this. So you want to minimize over the space of Hilbert-Schmidt operators this expression here. So this with respect to the least squares. Okay, and so then there is a classical approach. Okay, you do this here again with penalization or rich regression. It has a very nice explicit solution. You can solve this problem, in fact, and you can define with regularization, sorry, your approximate solution to the conditional mean embedding using your IID data here. So this is then also, so learning the operator here in this case is also boiled down to learning now a function, and you can approximate again your operator by using this learn function for the conditional mean embedding. So this was in fact the start of our work, and also in this paper here they derived some learning bounds which are also very classical and comparable to what is done in non-parametric regression when you choose your regularization parameter accordingly. And what we were asking here at this point, okay, you can at first, can we generalize the approaches of regularization for learning linear operators? What is the learning framework behind all this? Is there a general framework? And also, can we develop a theory which not only considers rich regression, but also other types of regularization? So gradient descent method, acceleration, and everything which is just which is known under the name of spectral regularization methods, which comes from inverse problems, in fact. And so we started to analyze this framework, and I restrict myself here now for only to learning linear operators, having in mind a little bit that this is maybe not anymore this up to date. So because you have now all these powerful tools for learning nonlinear operators using neural networks. But still, this framework is really nice what we got. And so I want to show you now how you can solve learning linear operators by just considering a non-parametric regression framework, and that you can get in the end, in fact, optimal learning bounds for a large class of regularization method at once. So let me introduce the general setup for now. So I consider two Bochner square integrable random variables, and they have values in Hilbert spaces, separable x and y, and they are random variables, or this is a pair of random variables with a joint unknown distribution. And we formulate the problem of learning linear operators as a regression problem. So where I want to minimize here the expectation of this square distance here, and then minimize over the space of linear bounded operators between input space and output space. So later we restrict ourselves just to minimizing over the space of Hilbert-Schmidt operators. Makes life a bit different, a bit easier, because we are dealing then with Hilbert spaces instead of Banach spaces. But just this for technical reasons at this point. And the problem here is compared to ordinary, so I call it ordinary or classical regression problems, is that if at least one of my input or output space has infinite dimension, then so does the search space has. And this causes some challenges in the mathematical analysis. And so again, so we are motivated by, at first by the example which I showed you about conditional mean embeddings, but also what fits in our framework is again functional linear regression with functional response, and also non-parametric regression with vector value kernels, and also inference for Hilbertian time series, and any other framework which involves learning linear operators, of course. So our approach is that we propose an inverse problem framework that generalizes finite dimensional ridge regression and all the other spectral cut-off and gradient descent regularization methods. So let's see how we can do this. So in contrast to the finite dimensional linear regression problem, the infinite dimensional problem does not necessarily admit a minimizer. And so we have also to make sure that everything is still well defined. So for linear models, if there exists a linear operator, such that we have a regression problem that looks in this way here. So we have an error term which is conditional on the input has mean 0, then our regression problem can be solved via a so-called operator factorization problem, which involves again the covariance operator and the cross covariance operator. So we have seen in the example for the conditional mean embedding that these operators are particularly useful for defining our regularized solution in the end. And also the operator factorization problem here again involves our covariance operators, which is very nice. So we apply here this theta star, so we use a theta star missing to our covariance operator, and this equals the cost covariance operator. And somehow to find this theta star here, we should somehow invert, solve an inversion problem here. Okay, and so we do this by introducing some theory to make everything look nicely. And we introduce here the precomposition operator. So when I have given an operator C, which is bounded on my input space, then I can define a new operator, which is associated to this operator C that maps a bounded operator into bounded operators, which is just given by multiplication. So we call this the precomposition operator associated to an operator C. And then, which is really a one-liner, you can the operator factorization problem reformulate in terms of a linear inverse problem very easily. So this is just the same expression as the OFP from the slide before. But the problem here is that it can be at first potentially ill-posed. That's not the problem. The problem here, in fact, is that this operator here is generally non-compact. So we know how to solve ill-posed problem which involve compact operators. There are many techniques available, and this is basically okay. The struggle here is, okay, how do we solve this inverse problem when our operator which we want to invert is non-compact? And that was the struggle in our work. So inverting here this non-compact operator gives our theta, in fact, which we want to find in the end. Okay, so this comes in a minute. So at first, we also need to make sure that our inverse problem has a solution, and also that this solution is somehow related to the regression problem which we introduced previously. And so we have worked on this problem, and we found out that there exists an operator which is bounded, solving the regression problem if and only if the cross-covariance operator belongs to the range of our precomposition operator associated to the covariance operator, which is a very nice theory here. And but still, also we have here is exactly what we need, namely the set of solutions of the regression problem is exactly given by the solution of the inverse problem, which is also very nice. So we can reformulate the regression problem in terms of an inverse problem. And we found out that we even have a little bit more. We even have a closed form solution for the regression problem. And this is given here exactly by this, what we have seen before in the context of conditional mean embeddings. This is given by here this generalized inverse of the covariance operator, the cross covariance operator, and taking the adjoint at this point. And here, again, we can be very hopeful when we know this. So because we can now think about, can we introduce also regularization methods, even though the operator we want to invert is no longer compact. And this is also great that we see here again popping up the covariance and cross-covariance operators, because for them we indeed have empirical approximations, which is also great. Okay, so coming now to identifying the empirical solution and also giving you a well-defined definition of the empirical solution. So assuming now here again that our regression problem has a solution, and here I mean the Hilbert-Schmidt regression problem. So I consider now only minimizing over the set of Hilbert-Schmidt operators and no longer just bounded operators. So then our solution here again is also given by this operator, and this is in fact the generalized inverse of our cross-covariance operator applied of our precomposition operator applied to the cross-covariance operator. And also what turns out very nicely is what you would expect also here is that this solution is the unique solution of minimal norm in the space of Hilbert-Schmidt operators. But the problem here again is how can we apply regularization methods when this operator A is not compact, and we need somehow get involved our covariance operators at this point. And what is regularization in general? So just to remind you here, it is just a strategy that involves a regularization parameter. It can be very explicit, like Tikhonov of regularization, or what we call implicit for gradient descent. So somehow we want to apply a regularization strategy, which is nothing else than a function here, to an operator which is non-compact. And when our regularization parameter tends to 0, then somehow this operator, which you need to define still here, should approach the generalized inverse in some given sense. And what we consider here as a class of strategies is the class of spectral regularization methods, which is super classical in the context of inverse problems. And it not only contains Tikhonov regularization and gradient descent, but also iterated Tikhonov, spectral cutoff, heavy ball, and Nesterov acceleration, for example. So there's a lot of work done already in inverse problems and supervised learning problems for applying these methods. And we now want to apply these methods also for our inverse problem with a non-compact operator. And now here comes the trick, what we want to do. So typically for compact problems, how we define applying a function to an operator for compact operators is that we classically use the eigenvalues or the singular values of the operator, and everything goes just over the spectral theorem, right? So we apply also the spectral mapping theorem. But this is no longer possible when the operator in fact is non-compact. But it turns out, after doing some calculations here again, that we can give it here a well-defined meaning by considering here the precomposition operator associated to applying this function g to our covariance operator. And now remember, the covariance operator is a compact operator. And defining here, so what I want to do is I want to apply a regularization strategy. And I can apply this strategy, of course, to any compact covariance operator. And even more, I'm in a lucky situation because I have an empirical approximation. And so I can also bring our data into play here. And this is a super nice formula here. So I really like this formula. It is the best formula in the whole paper. So because it solves our problem very practically at this point. And so we can bring into solving this inverse problem again, just regularization involving our covariance operators. This is very nice. And so now the regularized solution or empirical solution is just given by here applying now this regularization strategy to the precomposition operator associated to our empirical covariance operator. And this looks quite nicely like this here. And just as a reminder, empirical covariance operators are just the empirical approximations of the expectations here, which I introduced before already. So this is our formula here and our way to go. So everything is now really manageable. So because I boil down everything onto terms which I know. So I know the strategy, this is chosen by myself, and I also know the empirical covariance operators. So for deriving learning bounds, and this is super similar to classical non-parametric approaches also in the kernel setting, is that we need some kind of a priori assumptions. And this is also super similar to inverse problems or solving inverse problems. So one assumption is that for the solution we want to reconstruct, we need some kind of what is called a source condition. So this means we need to impose some smoothness assumptions for the function we want to reconstruct when I speak in terms of non-parametric regression. So for non-parametric regression, we often assume, okay, so our regression function is either linear or belongs to some other smoothness class, belongs to some subwave space, or is just in L2, or belongs to a reproducing kernel Hilbert space generated by a Gauss kernel, for example. So then it would be very smooth. And we also need some similar assumption here for learning operators, even though the interpretation maybe is not as straightforward as we have for non-parametric regression problems. But still, I want to give you the assumption which we impose here, which is the analog of what we call a Hilbert type source condition. So I assume so that I have given a source set, and this source set here again consists of powers of my precomposition operator. And recall, powers of my precomposition operator are well defined again by this formula here, which I have introduced before. And also, so I need to consider here bounded norms again. And this is some kind of pre-compact set, which makes learning even possible. And then we get super, super nice learning bounds for two different types of norms. And so as in any regularization problem, we need to choose the regularization parameter in an optimal way. And it involves here the power of our source condition. And then it goes classically like 1 over square root of n. So you just can think of the classical choice we know from non-parametric regression. And then I want to have learning bounds for two different types of norms. The first one is, so I consider here powers of my covariance operators. If the power is equal to 0, then I end up with the classical reconstruction error bounds. In case my power here is equal to 1/2, then we end up with what we call the prediction norm. And this is both given in Hilbert-Schmidt norms. So we have one formula for two types of reconstruction problems, as for reconstruction and also for prediction, and also for any interpolation norm in between, even, although the interpretation here is again maybe not straightforward for supervised learning problems. But what we get here is in fact also a rate of convergence, 1 over square root of n, depending on smoothness and the norm we apply, with high probability. And this in fact is the same rate of convergence we would get for classical non-parametric regression problems, which is super nice at this point. One could also improve this rate of convergence by considering again eigenvalue decay of the covariance operator, which is also done classically. So if you impose polynomially decay or even faster decay of eigenvalues, you can refine here these rates of convergence and also the choice of the regularization parameter. So this is currently not done. So just as maybe some background information here, so we restrict ourselves to random variables that are sub-Gauss and finding out, or so right now I could not find out how the eigenvalue decay with respect to sub-Gauss variables really is. So we believe it's exponentially, but a proof is left open currently. So maybe it's done already because it is somehow a straightforward question everybody working in this field maybe has, and maybe it's written somewhere, but we need to find it out at this point to even give more refined bounds here. So this is for now everything I have. So I hope it was not too fast and gives you some general insights into this type of learning problems. And so the take-home message here is, so because referring permanently to non-parametric regression, that predicting an infinite dimensional random variable is just as hard as predicting a finite dimensional random variable based on the information I have given in my data. So this is what you can get out of this, what I have presented today. So we have a preprint and we're currently working on including also the lower bounds in this setting to really get proof that these bounds are optimal in a minimax sense. But again, they match the minimax bounds from classical non-parametric regression settings. So we very much think that these bounds are in fact minimax optimal. It would be strange somehow if not. So thank you very much. So this is basically everything I wanted to tell you today.
Still have some time for I guess if there's no questions, let's thank the speaker. Thank you, Nicole.
Thank you very much.